Chapter 6, Section 6, Solving Rational Equations. So, after working with all these different methods with rational expressions, or complex rational expressions too, now we have all the tool set we need to deal with solving equations with these types of expressions in them. So, we talk about rational equation. We have an equal sign. And what we're looking for again is a solution. When we get an equation with one variable, we should be able to find a solution to that. And again, solutions are things that make our equations true. And I can't emphasize that enough. That's why we check, and that's our goal, is to find out what value can I replace that variable with to make both sides equal. That makes it true. So they give us some examples here. And one of the key things, and it's a very important thing, is when we have fractions that have a denominator with a variable in there, we have some restriction issues. In other words, we have to watch out for division of 0. And a quick little reminder about why we can't divide by 0. If you think about multiplication as multiple adding, and multiplication and a division are kind of like opposites of each other. Well, multiple adding for multiplication, what would be multiple what for division? Would be multiple subtractions. So when I say, 6 divided by 3, I'm asking how many times can I subtract 3 from 6 to get to 0? And in that case, it'd be 2. Or the idea of a remainder makes sense when you think about it that way. If I say 5 divided by 2 is, I get 2 2's I can subtract, and then I have 1 left over before I get to 0. I don't have any more 2's to subtract, or that's called the remainder of 1. Okay? Well, put that in terms of subtraction of zeros. If I have 5 divided by 0, that means how many zeros can I subtract from 5 to get to 0? Well, when you think about that and you're asked that question about what would happen in that situation using really the proper definition of division, you're going like, that makes no sense at all. In other words, that's why it's undefined. We do not it makes no sense to allow division by 0. It just doesn't fit into what division is. So, well, with that, we have to watch out for it. So, like in this case here, I don't have any issues here. I have no variables in the denominator. I have no possibilities of any value that I put in for x ever causing a division by 0. So no problems here. Let's look at this one. T plus 7 over t equals negative 5. Yes, there is a value for t that would be a problem. If I put 0 in for t, that would make 0 plus 7 divided by 0, which is undefined. I can't do that addition. Not that it would even look like it would make it true, but at that point, it's undefined. So I cannot use t as a 0. In fact, I would list the restriction as t cannot be equal to 0 just based on what I'm seeing in the original equation. In this one here, I have some issues too. I got a variable in the denominator. It's an expression here. So what value for x would make a division by 0? If I put 1 in for x, I'd get 1 minus 1, or I get a 0 here, and a 0 here is the same. So I would put a restriction in here that x, in this case, x could not be equal to 1. And that's what they're talking about here in the steps. First, list any restrictions that exist. Numbers that make the denominator equal to 0 can never be solutions. Then we're going to clear fractions by multiplying both sides by an LCM of the denominators, or an LCD, would be another way to say that. Solve the resulting equation by using the addition principle, multiplication principle, and the principle of zero products as needed. Check for possible solutions in the original equation. So there's our strategy for doing this. And then it says when clearing an equation of fractions, we use the terminology LCM instead of LCD because LCM is not used as a denominator in this setting, which makes sense. Okay, let's look at what they're really talking about here. This expression here, or this equation, excuse me, is x over 6 minus x over 8 equals 1/12. Now, do I have, that first thing, do I have any restrictions? Do I have any possibility of values for the variable x in this case that'll give me a division of 0? And in this case, no, I don't. Remember, we're talking about the original equation. Look for restrictions. No problems here for restrictions. And that's what they're talking about. Because no variable appears in the denominator, no restrictions exist. And then they say, well, what's the LCM between these denominators that are here? Because what I'm going to do is find the least common multiple. If I multiply both sides, basically I'm going to get rid of all the fractions if I use that LCM. In this case, it's 24. So I take 24 times both sides of the equation. That's just the multiplication principle for equations. So I can multiply by anything I want. As long as I do it in the right way and multiply and make sure I distribute, I can do that. But we want to do that strategically by using that LCM, and here's why. As I multiply this over both sides of the equation, I end up with the fractions going away. 24 times x over 6 is really, this 24 is 6 times 4. I end up with the 6's cross canceling, I get 4 times x. 24 times, if that doesn't happen, we know we picked the wrong number to multiply by. And actually I criticize these first examples a lot of times because they don't show all the steps, but how did we get 24? Hopefully you use prime factorization to get your LCM of 24, and then I would leave that. Think of 24 as the LCM as the prime factorization, which is 2 times 2 times 2 times 3, and then I would see that this is 2 times 3, so the 2 and the 3 go away, leaving 2 times 2 times x. Okay, same thing here. I end up with negative 3x. 24 times 1/12 is 2. So I end up with this new equation of 4x minus 3x equals 2. Combine like terms, I get x equals 2. Now there's no restrictions, so this has no problems as a possible solution. Well, how do I really want to make sure if I have a solution or not is I check that. So if I put 2 in for x, I get 2 6 minus 2 8, and I want to know if that's going to equal 1/12. In this case it does. And then they got to recall here, it says multiplication principle states that if I have a equal to b, it is equivalent to a times c is equal to b times c, as long as c is not 0. They basically restate the multiplication principle. And also, I think this is more like a caution, but this is strategic. You don't want to check into some new equation that you made by like multiplying by the LCM. Go back to the original equation, substitute in what you think is a solution, and see if it works. That's what they're talking about there. So let's look at example 2 here. A. I got 2 over 3x plus 1 over x equals 10. Now what do we start with first? I want to look for restrictions. Is there any values for x that could create a division by 0? Yeah. If I put 0 in for 3x, I'm going to get 3 times 0 is 0. I got 2 divided by 0, undefined, doesn't work. Here I got x in the denominator, 0. If I put 0 in there, I get 1 divided by, so both of those x equals 0 is a restriction. So first we state this. I would put in here basically at the beginning of this, I'd check that, and then I would put x cannot be equal to 0, x is not equal to 0 by putting that slash through the equal sign. And then I start solving this thing. And again, good strategy is what's the LCM between 3x and x? It's 3x, so I multiply both sides times 3x. Make sure I distribute, simplify as I'm going, and I end up with 2 plus 3 equals 30x. So I solve this for x by taking 1/30th times both sides, and I get x equals 1/6. Now, what was our restriction again? Is x cannot be equal to 0? Well, I think this solution is 1/6. They didn't hit some restriction. So I'm going to test this. I think I have a solution, and then I test that. So then we put in 1/6 into this original equation, put 1/6 in for the variable, and you get this thing right here, which is you end up with 2 over 1/2 plus 1 over 1/6. And what they do is treat each one as a division, invert and multiply. 2 divided by 1/2 is the same as 2 times 2. 1 divided by 1/6 is the same as 1 times 6 over 1, or 6. So I end up with 4 plus 6 equals 10. Okay, that's true. That is the solution. For this one, we're going to look at, we want to solve x plus 6 over x equals -5. Well, look for restrictions first. Note that if x is equal to 0, we got a problem. So restrict that. X cannot be equal to 0. Well, the only fraction I have is 6 over x. So the LCM for that would be x. So I'm going to multiply both sides by x. To get rid of that fraction, I end up with x squared plus 6 equals -5x. Well, I have variables on both sides, and I have a degree 2. Whenever I have something other than a degree 1 polynomial involved, I'm probably going to have to use the principle of multiplication by 0. So what we do is we add 5x to both sides. I end up with x squared plus 5x plus 6 equals 0 by using that addition principle, adding 5x to both sides. Well, I have something equal to 0. If I can get factors or parts of a multiplication equal to 0, then I know either one of those has to be equal to 0 or both of them equal to 0 for that to actually get a product of 0. That's a product of 0 thing again. So I factor this. This is not a perfect square trinomial because 6 isn't something squared, so I use reverse FOIL or anti-FOIL or grouping. And I factor this to be x plus 3 is one binomial times a binomial of x plus 2. Well, for this multiplication to be equal to 0, then again, x plus 3 has to equal 0 or x plus 2 equals 0. You solve those. I got x is equal to -3 or x is equal to -2. Well, then I check against restrictions. Hey, 0 is the only thing restricted. So there's a possibility I have two solutions. I check that by putting in here -3. Hey, it ends up true. Put in -2. That ends up true too. So I have two solutions for this equation, which are -3 and -2. Now, the examples just keep getting a little more complex, and I'll go through a couple more here. Basically, we're going to look at some things that, where you might find a solution that's equal to the restriction. If that's true, then we have no solution possible for that equation. But let's look at A here. Example 3A. I got 1 plus 3x over x plus 2 equals -6 over x plus 2. And I look at this, first I look for my restriction, which would be x is equal to -2 is a problem, so I say the restriction is it cannot be equal to that. And then to solve this, the LCM is x plus 2, so I take x plus 2 times both sides. I end up with this new equation of 4x plus 2 equals -6. Add negative 2 to both sides. Take 1/4 times both sides. I get x is equal to negative 2. Well, I have a restriction that says I cannot use negative 2 because I end up with division 0. At that point, I could say, hey, I found a solution. I got a restriction that says that it doesn't work, so I have no solution. But they go through the check anyhow here. They say, well, what if I did check this for negative 2? I put negative 2 in here. I'd end up with 1 plus negative 6 over 0, and you end up with negative 6 over 0. I'm going like, what do I do with this? Because if you put that in your calculator, if you ever forget this, put negative 6 divided by 0, and what it'll say error probably, and or no solution. So in this case, there is no solution to this equation because what I solved it for looked like you have to use the restricted value, which is not possible. Now B, they use, we have a little more complex LCM to multiply, but I also have some restriction issues. It's kind of nice that this is x minus 5 and x plus 5. Well, this is difference of squares, which factors into x minus 5 and x plus 5. So we find that the restrictions in this case are positive 5 and negative 5. Can't be used. So they use the LCM, which is this factoring of this difference of squares, and multiply both sides. Notice that they left things in factored mode, right? Because hopefully you'll see it cross cancels correctly and leaves some things to multiply. Definitely the way to go. And we end up with, we distribute that and do the addition. We end up with 4x plus 10 equals 2. They have a good explanation of what's going on there with the distributive property, and we solve that, we get negative 2. Well, what were our restrictions? Were 5 and negative 5 are restricted, so negative 2 is not. Looks like I have a possible solution, so I should check that. Okay? And example C, we have x squared over x minus 1 equals 1 over x minus 1. Note that if x is equal to 1, we got a problem, right? Actually, if you think about this, some of you already know the solution to this. It's nice when the denominators are the same, but we'll go through this anyhow. How can I get x squared equal to 1? Well, I could use negative 1 squared, and I'll get 1. Or I could have 1 squared, and I'll get 1. Well, I got a problem with 1. Some of you might be able to catch, hey, this has to be negative 1. But you may not. So let's go through this. And they take the LCM. Notice the restriction again is negative 1. They multiply by the LCM, which is x minus 1. They get x squared equals 1. It's kind of what I jumped to right up here, right? And which is, what do we do with that? Well, I have a degree 2, so I add a negative 1 to both sides. I get difference of squares. I can factor that. These factors are equal to 0. So I end up with two solutions of x equals 1 or x equals negative 1. Hey, 1 is restricted, so the only solution that works is negative 1. Okay, then they go through this checking concepts, which is more about, remember what you can do with equations and stuff. Some pretty good stuff to go through. And that kind of sums up here. They go through some exercises, but that's really, so we've taken all this different tools that we have about working with rational expressions and how we can simplify them using different methods and strategies, and then we're going to apply this to equations, and then hopefully we're going to be able to solve applications, since we have no restrictions on anything that's like a complex rational expression now.